Okay, good morning everyone. So today we are going to, since like I think everyone has a general idea after the 3 days of the sessions, like about the big picture of the machining dynamics, right? So before we go through the details, I would like to share with everyone about some like the flow chart of like what is the machining dynamics about. Then we go like what's the difference, as Dr. Low just said, between conventional and micro. What's the difference we need to emphasize by analyzing this process, okay? So first, since the workshop, the name is machining dynamics, right? So basically machining, we know it's a material removal process, right? So then it becomes a process dynamics. So it's based on, basically there are two branches contribute to this subject. First, the process. Process dynamics is different from structural dynamics, right? So yesterday everyone did this model testing, right? So this follows this structural dynamics area, and it contributes to one branch, okay? Means any mechanical structure has certain natural frequency, damping, and stiffness. When certain periodic or any excitation applied on a structure, it has either a transient or periodic steady state response, means the vibration. And this process itself also has mechanics aspect, right? So because it's a machining process, the tool goes through this workpiece, then it causes the deformation of the workpiece at this cutting location, right? So in the solid mechanics point of view, there's a terminology for deformation, means the material will have strain, right? So when the strain occurs, it causes, because everyone knows this is stress-strain curve, right, from basic elasticity or plasticity, then the strain causes stress occurs inside this material. As we know, the stress has a unit of megapascal or pascal. And if it happens in the area, it generates force, right? Cutting force. Then from the strain goes to the force. It belongs to the mechanics part. And dynamics, as we know, already know, like we have natural frequency, damping, and stiffnesses, right? All those two branches finally goes to this machining dynamics. And of course, chatter is one of the major issues in this machining dynamics. Of course, there are some areas, but chatter is the main focus, okay? So detail of this later slides will focus on this flow chart, but in a micro level, okay? Again, I want to mention that the content inside the slides is mainly based on my PhD research work. So it doesn't appear in any textbook or any other thing. So, and also there are several equations inside. But generally, I hope everyone can just try to understand the big picture, not to go through the details of the derivation of the equations, okay? But if you have any further questions, we can always discuss after the session or in the future. Okay, so first, it's a little bit of introduction. Like the micromachining, by the definition, it's mainly used to make the micro parts, right? So basically, some applications like the biomedical or optics, electronics, such as like sensors or something like, or for the automotive or sensor industry. Sometimes we want the system to be as small as possible because then it requires less power and it's more easier to operate. So basically, those are some typical parts in the medical or such as like the micro impeller. Okay, so like mainly used to, for example, in the fluid, right, applications or the fuel injectors. So those require drilling of the deep micro holes, okay, on the parts. Of course, like when we see this one, it's really like it's small in the small scale, but at the same time, it requires very complicated 3D geometry, right? So as we know, from the MEMS point of view, there are also several techniques to making micro features. Micro, we know like maybe 10 or 100, basically below 1 in the millimeter level, okay? One common feature is photolithography process. We have the UV light and trying to etching some materials on the base, right, to generate the very precise and accurate process. But this photolithography is mainly used for silicon-based material, okay? And it cannot be applied for different variety of material. Like sometimes we need the material to be like the steel, titanium, or even some brittle materials like glass, okay? Those cannot be achieved by the like this photolithography or the ion beam etching process. Instead, this is micro milling because it's just like mechanically remove the process, right? So it can be applied for different types of materials and generating the complex 3D geometries, okay? I don't want to say, I mean, each of them, they have their certain disadvantage and advantage. Of course, the photolithography or some other etching process, it has a very higher accuracy compared to mechanical. But this, like micromachining, it can be used in the more wider area. So I would say that will be the mainly difference between those two typical processes for generating microstructures. Okay? So now let's take a look at what's the major difference of fundamental aspect between conventional machining and micromachining. Okay? Here shows kind of a picture between the conventional mill and this micro mill. Okay? So basically, we define the micro mill. It's the diameter. This is the typical geometry of the micro mill. It always has a shank around 1/8 inch or around 3 millimeter. Okay? That part is clamped by the chuck, okay, tool holder, which is attached to the spindle of the machine tool. Then it has a taper structure. The only part which is in cutting with the material is this very tiny flute tip. That diameter of this flute, normally it can range from 10 to 1,000 or 10 micron to 1 millimeter. Okay? So basically, the typical diameter can be as thin as a human hair. But we want to use that material, to use that part to cut some very hard material. So you can imagine this challenge because if the tool becomes small, then if there's impact due to the process, then it generates a lot of vibration or the stress on the tool. Then it can easily break the tip. Even we cannot find out, but it always can generate also the very fast tool wear and cause a tool breakage. As a result, so also it influences the surface quality, right? So then, based on that, it requires us to, based on the geometry of the micro cutting tools and a certain material property, we want to predict the cutting force and the mechanics part, and also we want to identify the structural dynamics at this small tip, right? So based on that, we're able to analyze this machining dynamics, okay, of this micro cutting process, okay? So now, I assume everyone is now familiar with this figure, which is a typical orthogonal machining process, right? So based on the classic mechanics model, we always assume the tool is perfectly sharp, right? Then when it goes through the workpiece, and then the workpiece, the uncut chip thickness with the material has certain deformation along this, we call it shear plane, right? So, and there is called an important angle called shear angle, right? So, which determines the orientation of this shear plane. Then the material becomes like a chip to form the chip and then leave this rake face. So then we can use, I mean, this is a classic merchant theory which was developed like 1945, right? So to characterize this mechanics part. But as we know, like no cutting tools is perfectly sharp. The only reason we assume it's sharp because in the conventional machining, the chip load can go above 300 microns. And normally for the milling edge here, the edge radius I say it's 40 microns, but normally we can really grind it to be less than 20 microns. So then it's basically 1/10 smaller of this chip ratio. Therefore, like from the mechanics point of view, we can treat it as a perfectly sharp by assumptions, which doesn't affect the result quite a bit. But now let's say in the micro level, normally we cannot have 300 micro chip load. Then it will break to immediately, right? So normally for the chip load, it in the range of 5 to 20 microns. But at the same time, based on the process limitation, we cannot make this edge in the same ratio to make it as the same ratio smaller as the chip load. Again, the chip load, the edge radius of this cutting tool always is above 5 microns for micro, even for micro carbide tools. But for micro diamond tools, it may be a little bit smaller, but the carbide tools will be the main applications for us. Okay, so then we can see both. We just try to reduce this edge, which finally is in the same scale of this edge radius, right? So now we cannot really neglect the edge radius effect. So now it becomes a dull tool, a round edge. Okay, it's not because any tool wear or the process makes the tool dull, but only we reduce this edge. Then we cannot reduce this edge accordingly. Then it becomes a round edge radius. Okay, during the cutting tool. Then when this edge radius is in the same level of this uncut chip thickness, then it changes most of the material deformation mechanism. Okay, we are going to analyze. I mean, when comparing between the conventional machining and micro machining, there are two major differences. One is this edge radius effect, okay, and another one is from the material side. Material side, again, there are two branches. One is when the material is become very, very small, there's a size effect. As we know, when the material goes to maybe like sub-micro level or nano level, the strength goes higher, right? And second is, we know most of the metallic materials are crystalline structure, has crystalline structure. Then it has certain grain. For example, like the 1045 steel, it has like the ferrite or perlite grains, phases, right? And each grain is always also in the range of 5 to 10 microns. Then all the heterogeneous property of the material side also contributes to the difference between the micro and conventional cutting. But for our case, especially for my own research, we are mainly focusing on the edge radius effect. Okay, so that will be the main part. So now let's say we have the round edge, okay, of the cutting tool to remove this material. So basically, if its tool is super sharp here, we can assume the material suddenly deforms from its original formation to the chip, right? Just at this thin layer. Even with the sharp edge, like actually it's in the small band, but the thickness normally for simplicity we neglect and treat it as just a plane. But if it's become edge, basically it enlarges this material deformation zone to be a certain thickness. Okay, which cannot be neglected. Then what happens is for the material, it moves in this direction from the workpiece side and gradually has certain strain, okay, has certain strain along this line, and so finally form the chip, right? So inside, let's say from the bottom to the top, the strain is different, okay? When the strain is different, and also the strain rate possibly can be different, then the stress possibly can be different for any point in this wide range of this material deformation zone. Another point is that since this edge is not sharp anymore, some of the material which is below this dashed line here, when it goes to, and basically it goes to the bottom of this edge, then finally it's going to be suppressed down, not form the chip, but suppressed down to form the chip, okay, which is natural, right, from the intuitively. Then what happens is we have to define a stagnation point where upper part of this material form the chip, but below that it forms the surface finish the surface, okay, which we say is more like the plowing effect. And above that, we know from previous sessions, like it's called shearing phenomena, right? So That's a major difference from the fundamental aspect, trying to analyze the difference between the micro and the conventional machine. Okay. Also, if you have any question, you can just stop me anytime, so I can try to clarify. Okay. So then it brings us the objective. Okay. So now we cannot use the classic mechanist model or merchant theory to predict the cutting force, right? So then, how do we do that? Okay. So now we want to, based on the material constitutive model. We mean the constitutive is that any material has, when it deforms, right, it has certain stress, as I explained here. Then the stress, of course, depends on the strain, right? So this is a typical stress-strain relationship. And this strain line means elastic deformation, right? So what's the meaning? What's the physical meaning of the slope here? Young's modulus, right? Elastic modulus. Okay, great. Then, at this point, there's a transition from the elastic to plastic region, right? So then, this plastic it also increases with the strain, which we say there's a strain hardening, right? Because for the machining, we know it has even it happens in a very small region, then it has a very high strain because it involves large deformation. And also, from this constitutive model, actually we can normally, like when we want to obtain this stress-strain relationship for certain material, how do we do that? We just put it in the tensile test instrument, right, to give certain stress and measure the displacement. Then we're able to get this curve. But those data is not able to be applied for machining. Okay? Why? Because the machining, the process, because of the high cutting speed, this deformation happens in a very fast rate. Okay? Then this strain rate in the machining can go up to 10 to the 4th or 10 to the 5th. But in the normal, like the tensile, the strain rate is normally like 0.1 or something like that, very slow. Therefore, like the normal tensile test, we cannot get that stress, okay, from normal test, okay? And then, so also, like because it happens so fast, there's a temperature rise inside the material deformation zone. Basically, for the machining of the steel, right, we know the temperature even can go up to about 1,000 degrees Celsius for conventional machining. So when temperature goes high, we know temperature has a softening effect on the material, right? When temperature goes, the material basically becomes softer. All those influence this stress-strain relationship, okay? And then, based on the flow stress and based on this two geometry here, it contributes the change of this cutting force, right? Of course, also, because of the dynamics, okay, dynamics of the tool at this small tool tip. Normally, if the structure of this tool tip, when the size goes down, we know what's the relationship between the natural frequency and the mass. It's inversely, right? Omega n is equal to square root of k over m, right? And when it goes lower, the natural frequency goes higher. But of course, it also relies on the stiffness. But generally, for the micro machining purpose, because of the small tool tip, the natural frequency of the tool tip can go much higher, which we cannot use a normal hammer test to obtain those property here. Okay? Then we need to develop a new strategy to obtain the same property. Okay? So that's also one challenge. Again, another process, another effect I want to talk about is called process damping. Okay? Later we're going to talk about that. This all because of this two round edge, which contributes to the change of the chatter stability. Okay? So basically, this is a flow chart, which is similar to here, but we just emphasize for the micro machining purpose. Okay? Again, based on the material constitutive model and the cutting conditions, I developed two models. Okay? One is called slip line field model, which based on the classic material plasticity. Okay? And I also developed equivalent numerical model based on the finite element method. So trying to predict the cutting force from the material property and to edge geometry. To edge geometry, which I mainly means edge radius here. Okay? And then the cutting condition, which is from the chip load, uncut chip thickness, and the cutting speed. Okay? Then based on that, we know to analyze the cutting force, we need to this cutting force coefficient, right? All those models contributes to the identification of cutting force coefficient, okay, based on those factors, okay? Then, if we know the mechanics part, for the structural dynamics, I try to calibrate the microcutter tool dynamics, okay, and analyze the process damping effect. And based on that, we're able to predict this chatter stability lobe, especially for the micro machine. Okay, so now we just start from here. What is this slipline field model is about? Okay, so basically, the slipline is based on the classic, like the plasticity. Actually, the merchant law, which assume one line of shear plane, that line is like the very special case of the slipline. But if we say here are several previous work on a similar field, and if we consider the two edge radius, we know that the material deformation zone becomes a region instead of a plane, right? So, and also at the same time, there are secondary and tertiary zones here, right? So, and also there are several other models, like considering if there's some change of this rake face, and it also changed the geometry of this material deformation zone, okay? But in our case, basically, we just want to first consider about the material property and also include this shearing and plowing effect due to this edge radius here. Okay, so here shows kind of this material deformation region. Okay, here's the green region is a primary, green one is a secondary. Okay, tertiary is in the red color here. So before we go through like the details, like anyone learns this solid mechanics know this stress Mohr circle? If not, I just like briefly talk about that. I mean, any material, okay, if it's under the deformation, we know inside, let's say if we just pick one point, for us it's a machining purpose, but it can be applied for any like the forming or any other material deformation process, okay? So all those involves, if you want to analyze the mechanics, it involves the analysis based on the stress Mohr circle, which means at any point, if there's a deformation, there's strain, and there's stress, and the stress can be analyzed by a circle from the orientation. Let's say we just pick one random point here, okay? Then take it out here. Like let's say it become a small region here, okay? Then the stress can be characterized by normal stress. We use sigma, right? And shear stress, okay? So from the application side, before we go through this, from the application side, if you treat this, if there's a plastic, okay, plane here, and if we use a like perfectly sharp or perfectly rigid, like a wedge, to press that, what's going to happen? Let's say here is a plastic, okay, plane, and we assume the friction. There's no friction on top, okay? And there's like the super rigid but like object to press that, then make it has plastic deformation, okay? So my question is, in which line, in which angle, if there's a material deformation, in which angle it will start to deform? It will just deform like down or in any 45 degree, excellent, okay? Basically, it starts to deform along this 45 degrees, okay? Why? We can analyze this stress Mohr circle here, because at this point here, because it's a boundary, right? So there is no normal, this orientation, the sigma normal stress is 0, and also the shear stress is also 0, right? So at this orientation, it's located at this point, okay? Then when it has deformation, we know the plastic strength, we say plastic strength is K, means at the value of k, it start to have this plastic deformation. Okay, then this stress-Mohr circle always has this circle of flow strength k. Okay, then if we just analyze the point, in this orientation is located at this point, but when it starts to rotate spatially, but again at the same point, we just see the stress distribution along different orientation. When it has certain angle theta, it moves by 2 theta, twice of that. Okay? So what happens is, from this stress-Mohr circle, if it's 90 degree, what happens is the shear stress reaches to the maximum, which is k here. If it's 90 degree, what happens to this point? It is half of this angle here. It's 45 degree. Physically, it means at 45 degree at this point, it has highest shear stress. That's why when it starts to deform, it happens at 45 degree. Okay? So the physical meaning of this stress-Mohr circle is that for specific point which has stress, we want to see the stress distribution along different orientation. Okay? Then we want to analyze at which angle it starts to deform, which always happens to here. Okay? So that's basically the concept of stress-Mohr circle from the solid mechanics part. Then this blue line here I draw is not randomly drawn. Okay? So this is based on certain plasticity theory. Okay? Which I'm not going to talk in detail, but those are called slip lines. Okay? So basically, there are 2 types of slip lines in any deformation region. We call it alpha line. Here's the alpha line here. And orthogonal to that, those are beta lines. What happens to this is that along this alpha line, it always, at any point, along this tangential direction of this alpha line, it always means a top point of this stress-Mohr circle. Then, when it goes to by 180 degree here, it becomes in the orientation of this beta line. Means when the material starts to deform, it always follows the tangential direction of this alpha line and also beta line here. Okay? So it means, okay, we just pick one point. When the material come to here, then what happens at this point? It starts to deform in this direction. Okay? Because along this tangential direct line, it has this maximum shear stress. Okay? Sorry, why is it always happening like that? And at this point, it deforms in the different direction. Okay? Because there's a curvature here on this alpha line here. Okay? It means normally, based on that, based on this edge radius, now the shear plane is not become a plane because a curved region. Okay, so that's the concept of this slip line field model. Okay, so but again, in the conventional slip line field model, we always think, okay, the shear, the flow stress K, the shear strength, is a constant in the whole region, but it cannot be applied in our case because we know when it goes, it starts to deform along this plane, right? Then the strain gradually accumulates. So therefore, when it goes to this plane here, it becomes a final shape. So it means at this point, the strain must be much larger than this point. It means we cannot treat it as a constant shear flow stress, okay, inside the whole region. We need to analyze the distribution, okay? So then, based on the material property, there's a well-defined model, which we call the Johnson-Cook constitutive model. Okay, this model is basically describe this sigma. Sigma means we say it's a flow stress. There's a relationship between this sigma and k. K is always sigma divided by square root of 3. Okay, so we just this is still based on the classic solid mechanics. Anyway, so now this sigma or the k is a function of epsilon, which is the strain and strain rate here. Strain rate, we can see based on different strain rate, the stress can be different, right? Also, temperature, right? So the temperature, when temperature goes higher, the stress goes to become lower, become the thermal soft effect. Okay, so normally people do this, use the called split Hopkinson bar, pressure bar. It has this material has a bar and gives some impact at different temperature. Then it's trying to calibrate the relationship between the stress and strain. And then based on the experimental results, we calibrate all the coefficient A, B, C, or the TM. Like TM is a melting point, and TR is the room temperature. But anyway, from that, we are able to know all the coefficients. Then based on any strain rate, and temperature, we are able to predict the stress here. Okay, so that's the concept here. And another effect we cannot neglect is the two workpiece contact point. I mean, from the first day of the session or second day of the session, from the classic mechanics part, we know the two chip contact, there are two regions. One is sticking, one is sliding. Why the sticking happens is because at this bottom part of this rake face, there is a very high pressure. Okay, then if some chip moves on a rake face, for example, on the table here, if we have very high pressure, and also this material are newly formed, right, because of the fracture of the material, then there's some certain chemical interaction between the material and the rake face. Then it's not going to slide. Instead, it will stick there. And then, and above that, other material flow above that, okay? Then when it goes up, because it's going to leave this rake face during the curve of the chip, then it becomes a sliding, which satisfies the normal Coulomb friction. Then we have to define this sticking and sliding contact. Again, based on different region, the shear stress here, tau, okay, which is defined by Mohr circle, is different. Okay, in the sliding, it has a Coulomb friction, mu, but in the sticking, so the tau is related to the stress, normal stress of the material. Okay, so basically, we need to calibrate the m and the mu for the machining process for different material. Okay, for this, basically, we try to do a few orthogonal micro turning process and try to measure this chip thickness. We know that the friction between the chip and the rake face, it influences mainly the chip thickness, right? So there's a if you like from the previous sessions, there's a mathematical relationship, right, between the chip ratio and this friction coefficient. So we try to identify these parameters, okay, based on the measurements. Now,
can you go back?
Mm-hmm.
How do you measure chip thickness in microton?
We still have this kind of very small shape, but we cannot measure the weight, because normally we measure the weight, right, and divide by the density. We know the volume, so then divide by the weight, we know the thickness. Then for this, we have to put it in the microscope or the SEM, trying to know the thickness in the micro level.
Did you appreciate that? We discussed how to identify chip thickness ratio, right? You can't do that here.
Yeah. Mm-hmm.
Okay. That was just a point.
Yeah. Mm-hmm. Okay. Now here here like in the next 2, 3 slides, here's a very details about this slate plan field model. So I just want to mention the general idea. Okay, so we don't need to go through the each equations, because it took me almost 2 years, okay, to get those equations. So basically, what happens is, because it's curvature, okay, we model this region by the polar coordinate. Okay, then how do we define the strain rate? Basically, the strain rate, we know it's related to the velocity, right? So then we think the strain gradually increase from the beginning to the end here, okay? Then how do we define the strain is that, let's say, here's an original material, right? If there's a shear applied, let's say this small rectangular is just the inside here. Then because the strain, it has small shear, it becomes like this, right? So how do we define the shear strain? Is this length, right? L1, just L divided by D. Right? So that's how do we define the shear strain based on the classic model here. Now, we say based on this model, this strain is here. The strain is always 0 because it still belongs to the original workpiece, right? Then the final strain, okay, is accumulation. It increases as a linear pattern, okay, gradually from the original to this end part, okay. Then we try to model this strain based on this polar coordinate. Then based on that, if the strain happens and strain times strain rate is, anyone knows what's, let's say epsilon is a strain, sigma is a stress. Stress integral with respect to strain, what's the unit? Or if I just make it force times distance, energy, right? So now force divided by the area is sigma. The S divided by length is strain. Now it's energy at unit volume. Okay? So then those energy contributes to what? When something deforms, right? Sometimes we feel the heat, right? If you bend a steel, it has strain. Then if you bend always, we will feel the heat at the deformation point. That's because when deformation happens, because this relationship, this contributes energy dissipation. Energy finally becomes higher temperature, okay? Then based on that, okay, so again, why do we? The temperature, that's why like sigma E contributes to the temperature increase, okay?
But there will be conduction also, right? So how do you account for that?
That's why. For this case, we don't consider because that's why we add beta, which contribute, like we use the 0.7 for different, I mean, I know there's an assumption,
so
but.
If you assume it to be adiabatic, I can agree with you.
Yeah.
Some sort of adiabatic you can do as no
you're right.
Then you can kind of use this kind
of Yes. I mean, the purpose is we're trying to develop analytical model for this. I mean, there are certain assumptions.
So, which is, for some materials, it's actually fairly accurate. If
you're
talking about nickel or titanium, I think it would be fairly accurate.
Yeah. That's right. That's a good point. Anyway, the general idea is based on energy. We add some coefficient to accounting some convection or the conductivity of this material. Then we are able to calculate the temperature increase. Then we know strain rate, strain, and temperature at any point inside this material deformation region, okay? So from that, we borrow this Johnson-Cook model, so we're able to know the stress of this material here, okay? So this two actually is related to the slip line like this, okay? Basically, along this slip line here, if we know the boundary condition here, we can follow this strategy, okay, to know the hydrostatic pressure, which, I mean, the center point, this P. This coordinate here, this value here is we call P. It means it's a hydrostatic pressure, okay? Which means at any point, if we know the center coordinate of this P and K here, we're able to draw a stress Mohr circle. We're able to know the stress situation in any direction, okay? So that's the idea. That's why we want to know the hydrostatic pressure and K at any point. Okay, so after that, we're able to know the stress situation or stress Mohr circle along any point on this two rake face and the two edge. Okay, so based on that, we're able to predict the cutting force. As we know, the cutting force is basically integration of the stress along the two edge, right? So that's basically the general idea of this prediction of cutting force. Okay, but again, this doesn't consider any dynamics part, right? So it's just the idea is like for the micro purpose, we're trying to use this like the material constitutive property and borrow this slip line field model and obtain the cutting force. And of course, we can always change the edge radius. We can always change the rake face. Basically, the reason we change, like if it changes the boundary condition of this field. Then
all the slip line models have been developed for a constant K, right? Where
yes.
you assume that K is constant.
That's a previous model.
Almost the entire slip line theory.
Yeah.
The 45-degree thing, because if there is K discontinuous is there, then
the
equations will probably, velocity graphs will change and things
You're
like that.
You're right.
So what I'm kind of thinking is, in your case, K is separate.
Yeah, K is different. That's why we modify this stress partial differential equation. Yeah. That's why it's kind of a change based on the, that's a major difference between this model and the previous model. Yeah, that's a good point. Okay, so now also, I mean, this slip line, basically, it's an analytical method, okay? We also tried to use the numerical method, finite element model, and trying to see what's the difference between the analytical and the numerical models here, okay? So here, maybe someone already has experience to certain FE softwares, right? So Abacus is a one general purpose FE software to simulate any like the machine deformation processes. So we use this model to trying to do the same thing for the machining purpose, and then we give a radius of at the two tip, and we model this workpiece. So then give a certain velocity of this workpiece, and then apply this friction property between the chip and the workpiece. Then we're able to simulate all this chip formation, and based on that, trying to calibrate the cutting force for the certain chip load. Okay, so again, there are certain some tricks. Okay, because the FE model is a general purpose. It's not designed for machining, right? So it's not like we just give some match of the two geometry and the workpiece, then it starts to run automatically. It's not like that, okay? Because if you think about the major problem comes from this small region here. Because what happens for the FE model is, let's say we try to first mesh anything, right, from the to be very small elements. So let's say there's a two geometry, and here is a chip here, right? So in the FE model, especially at this region here, the material involves very excessive deformation. And originally, let's say we just model like rectangular shape, okay? And if this original deformation, let's say this is original, okay? For example, if it moves to the left and this moves to the right, if it becomes like this, okay, in the element side, the simulation stops, okay? Then it says, okay, it has excessive dimension. It cannot handle this situation, okay? So what happens is, in the Abacus, we can use different meshing strategy, okay? Here we call it two meshing strategies. One is called Lagrange. The second one is Euler-Ring. Lagrange is basically, we always fix, I mean, there's a two topology of this process. One is meshing. Another one is material, okay? So in the Lagrange deformation, the material is always fixed with the meshing. But in Euler-Ring, we can release the material, but we fix the mesh, okay? Then the material moves, okay? But when it moves to another element, the element automatically grabs the property from that material, okay? So therefore, the meshing side, it doesn't change anymore, but the material does, okay? So here I want to show one animation to see it can simulate this chip formation here, okay? You can see actually the element here, it doesn't move, but the material actually moves. We can still find out the stress change at each point. Okay? So the advantage of this is it can simulate this chip formation from beginning to the end. And at the same time, if we record the cutting force, we can always see this evolution, okay, the change of this cutting force here. Okay? So basically, that's conclude this first two parts. One is based on analytical model, okay, and second is the FE model. For analytic model, basically, from all the equation, if you're able to put it in the MATLAB code, it runs in several seconds, okay. But in FE model, to run a situation like this, it normally takes about 30 hours, okay, for one simulation. And sometimes, if we don't mesh it very well, those deformation happens. After 20 hours, it stops. Okay, you have to run again. Okay, so that's why normally the students who works on this is they start the simulation, then they go back to sleep. Okay, then the next morning they try to see the results.
Excuse
Lagrangian in terms of machine? What's the difference between if I'm using Lagrangian and
Yeah, okay. Basically, in this machining, what we did is, I mean, different people have different strategy. For what we did is only in this red is covered by the red line here. Those are Euler region. Other ones are Lagrange region. So that's why the Lagrange region, it can simulate the moving of the workpiece and chip formation because it moves. But Euler region, it cannot move.
So in a shape chip, the elements will not deform.
Yeah.
Euler region. No
Yeah.
deformation will be there. So generally, fluid mechanics problems, right? People use Euler region because the fluid flows. And
Yeah.
the mesh will not change at all. In solid, pretty much people use Lagrangian because they need to see the deformation.
But if I'm interested on the chip shape or
Chip shape is coming, right?
Chip shape is coming, yeah.
Because that's why he has Lagrangian in chip shape.
Mm-hmm.
Only in the contact area he has a area where he wants to avoid deformation.
So in
Severe
the
deformation.
there won't be breakage of the elements.
No, the element will be fixed. Whatever shape will be there will be fixed.
Mm-hmm.
Lagrangian, the element starts to deform.
Then it stops.
So that's why
Yeah.
he is using that.
Yeah.
Otherwise, this code will not run.
Yeah.
It will be very difficult for you to run.
But it doesn't mean the material is keeping there. Material is still moving. Only the machine is stationary.
Elements will remain intact.
Yeah, yeah, yeah. But when you see the stress distribution, you can still see the stress, okay, inside this Euler region here, where it's moving. Yeah. Okay. So of course, like those are always based on a model, right? So we always want to do some experiment to verify that. Otherwise, the model is useless. Then I tried. Here is originally is a micro mini machine, but I treat it as a turning purpose. What happens is here is a small brass tube, okay, with the outer diameter is 6 millimeter, and the inner diameter, remember, is 4 millimeter. So that means is a tube. The wall thickness is 1 millimeter, okay. Then we have this small turning insert clamped, okay. The edge is facing upwards, okay. Then the spindle starts to rotate, and then it moves down. So it's mimicked to be a turning process. And bottom this is a very small dynamometer we are using, okay. Actually, the dynamometer has very good performance. It can measure like even lower than 0.1 Newton, okay. So it was no problem.
It's not mini type.
Mm-hmm. It's a mini type. Yeah, 9256. I remember. Yeah.
C2.
Yeah.
C1.
Yes. You're right. Mm-hmm. And now we put in the SEM to measure the edge radius here and try to do the simulation and compare with the results for different cutting conditions. And here shows the cutting force, okay, between the experiment. Experiment are the discrete dots here, and between the slip line and FE. Surprisingly, the slip line has accepted the result, but FE, especially for the feed force, is much lower than the experiment, okay? It means even the FE here, we can run it properly. We cannot not always trust the feed force result, okay? So, I mean, still we are trying to analyze the problem, but we found out the feed force is mainly coming from the friction, right? And we found out even like we apply the same friction property identified from slip line, the chip thickness, it doesn't increase as what we expect, okay? Then if the chip thickness doesn't increase that, then cause the very small change of the feed force, okay? So that's still a major work we are trying to figure out, okay? But basically, it gives us some idea. I mean, there's a feed force discrepancy, okay? Discrepancy between the experiment and FE model, okay? So, but anyway, like now we have those two models calibrated from the orthogonal configuration, okay? But our purpose is trying to analyze the micro milling process, okay? So then we want to calibrate the cutting force coefficient from the result. Then actually this is similar to the mechanics session, what we have learned from previous sessions. So we have different cutting force data predicted from the simulation, okay? Then because for very small region here, okay? For very small region here, now it becomes nonlinear, okay? Between the force and uncut chip thickness. It means we cannot use a linear model to characterize the whole uncut chip thickness range. Okay, so what we did is first we model this cutting force as a cutting force coefficient in tangential and free direction times the chip thickness and the width. Okay, then this cutting force coefficient is calibrated by a power functions of two parameters. One is h, which is uncut chip thickness, and another one is edge radius. Okay, basically from the simulation side, we're able to fit between this power function to the simulation results. Well, then we're able to get all the parameters, t or d, whatever, all those constants. Okay.
Any particular advantage I can do experiments and fit the same data?
You're right, but from experiment, we can only fix data for that specific cutting conditions, right? So, but for simulation side, we're able to for any range.
For different material, I will do different ideal material properties also.
Yeah, that's right. Yeah, that's right. Okay.
You need Johnson Cook parameters anyway.
Yeah. So
Yeah.
you can do experiments either on Hawkinses or something.
Yes. Yeah. Okay. So then after we have those, another problem for the micro mini is a tool run out, because even like for the very precise spindle, it always has certain run out, maybe from maybe 1 to 2 microns, even for the very precise spindle. But I mean, if the true trajectory is very small in the micro machining process, it's in the same level. Okay, that means we have to consider this tool run out. Okay, basically from my own experience, we still try to measure this tool run out from in the static way. We rotate it and using the dial indicator to see this, because the run out means if there's no run out, it's just rotate by its own axis, right? If there's run out, it's a little bit off to its center. Then when it runs, it has its self rotation. Oh, why this one is also rotating? Okay, it also has another rotation with a larger radius. Okay.
We've all seen run out. We saw
Okay, that's.
We saw 80 micron of run out.
80 microns. Okay.
Micro
80.
bigger than the tool diameter.
Okay, so yeah, basically this effective tool run out on the cutting mechanics is already well described. So now we just include this tool run out to trying to predict the cutting force. Okay, and however, the measurement is also a problem in the micro machining, because why? This dynamometer itself is a dynamic system. Okay, because for the micro machining, we normally use very high spindle speed. It can go up to 100,000 or even 150,000, right? Because we have because the small tool diameter, it has to reach certain speed to cutting certain material. Then it has to have very high spindle speed to reach that surface speed. Okay, so now let's say here's the measurement system. Okay, here's the workpiece. Here's the tool. Okay, the cutting happens here, and the force signal comes from this part. Then it goes to the charge amplifier, goes to the computer. We're able to see the force. Okay. However, and yesterday we already know this concept of frequency response function. Okay. Now even the measurement system, it has a frequency response function. Okay. So means if there's a static force applied here, we measure the same thing. But if it is a very high frequency force, okay, now we need to consider this frequency response function. What happens is the vertical axis of this frequency response function for the system is the ratio between measured force to originally happened force there. Okay? When it's static, when the frequency in the x-axis is 0, it's 1. Means whatever a static force applied, we measure the same thing. Okay? But if the frequency component of the force here, if it goes to 3,500 hertz, what happens is the y-axis, the y value here is around 30, which means if there's a sinusoidal force, okay, 1 Newton, with amplitude 1 Newton, but with a frequency of 3,500 hertz, then you will measure how much force? 30 Newton. Okay? So that's because inside this measurement system, there's always can be approximated by several spring damper system. Okay, it has its own dynamic limitation. Okay, so that's the main problem. Okay, so normally let's say here is the original, like actual cutting force we measured, like a little bit not clear, but if I say it's the range from negative 0.2 to 0.8 Newton. Okay, but here is the real measured force. Okay, first the amplitude is much larger. It's measured like from -1 to positive 2 newtons, and also it's highly distorted by the dynamics of the measurement system itself.
So you take the force output from that and then do the FFT of the force, is it?
Yes, yes.
But the you know that the natural frequency for this thing is about 4 kilohertz, 4.4 kilohertz. That's what they claim. But usually it's less than 3. How much you are getting?
Yes.
45.
This one is 3.5 at peak. Yeah. Okay. So what we did is, I mean, luckily there's our colleague who graduated before. They did for the spindle measurement, like they can use called a common filter, which is from the control theory. So if we know this dynamics of the measurement system, we're able to compensate from the actual force back to its original one. Okay, so I kind of borrow their algorithm, and we have this measured force. What I did is before each test, okay, we do this hammer test again on this. We hit this point, okay, and measure the force, but we don't attach any accelerometer. The response is coming from the measured force. Then we get the frequency response function for the measurement system itself. It's a force to force FRF, okay, not displacement to force, okay. So then if we know those two, we're able to use this algorithm to calibrate original cutting force, okay. So after that, we try to compare between the simulation and experiment, because the simulation, it doesn't consider any dynamics measurement error, right? So just from the experiment, now the blue one, the black one is actually measured. The blue one is common filtered, okay? Then we compare between the slip line and the FE model. Only there's a difference between, I mean, all of them has very small amplitude, right? Between -1 to 0.4, but there's percentage-wise, there's a wide discrepancy between the FE simulated and the real force over there. This, as you know, is because of the cutting force calibration, right? Because the feed direction has a certain mismatch between the FE and the experiment, okay? But anyway, so this gives us some idea, like at least for some certain force data, we're able to use the models, try to predict the results with certain accuracy, okay? So that's the idea. Okay, now we covered this mechanics part, okay? The dynamics part, again, there's a challenge from the hammer test. And this one, I think everyone is now familiar, right?
Can we go back one slide?
Okay.
Your cutting force coefficients that you get in micromilling, can we get them in milling and then use them in micromilling for the same workpiece combination, no, right?
Because you're not touching them with the
There's no
micromanage
tool.
effect, right?
Yeah.
There's no tool effect. So we have to identify it separately for this and then.
Because the uncut things which you are cutting, right?
Mhm.
ATLS effects will be there, side
Yeah.
effects will be there.
I know, this is for our participants. Right? So what we did, when we identified cutting force coefficients in turning and milling, we cannot use them in micromilling or micromilling. Let's do it again.
In a micromanage.
In a micromilling. Or a microturning.
Or something like this predictive model which is very high fidelity.
How to deal with noise, sir? Because both magnitudes are very small.
Noise?
Yeah.
At this level,
Because noise is actually bigger than
Was
force.
there any special experimental setup or?
What did you do?
because we bought very expensive dynamometer.
So everybody has the same dynamometer, trust me.
Okay,
Even
okay.
with that, there is a lot of noise. Right?
If we check this frequency response function, I mean, because from the, sorry, not frequency, but the FFT of this time domain data, actually, like we can see all the peaks. I mean, we can see verify the major peaks from at the tooth passing frequency. It's much higher than the others.
No, so you are measuring 0.1, 0.2 or whatever forces.
Mhm.
Your drifts will be like that if you just leave it in a little bit. So I think the basic idea is A, whether you want to take data in AC or DC, because DC there will always be a drift. So one way to do it would be if you take AC data. So drifts will die out. but then you lose your mean. So there are ways and means to do it. Plus, what you have to do is you have to make sure that there is total noise isolation. So everything that has a motor is as away from the
No talking noise.
data acquisition is going to be cost out. So you try to make sure and then see. You can also detect the drift. That if you just let it go, first thing is before you start a dynamometer, let it be there for 3-4 hours. So at least the drift goes away.
You saw this in the turning experiment. There was a drift in one component, right? Some batches saw this, right? Because dynamometer takes time to settle.
So just make sure that you run for some time, maybe a few hours before you start taking the real data. The drift actually stabilizes. Plus you have to make sure that everything is, wherever there is electrical noise, probably try to cover it with aluminum sheet or something.
Yeah.
So basically, as best shielding you can do. Make sure all the grounds are there.
Yeah.
But we have been able to get 0.06 Newton measurement.
Okay.
0.06.
Huh.
How do you trust that?
No idea. This is what we got out of it.
And this machine, they have to stay on the vibration isolated pad. And this machine, it has to be in the temperature, at least, I mean, not precise temperature controlled room. Okay? I mean, at least maybe plus minus 1 degree Celsius, which if you have the ventilation, it can be. Okay? So.
Sir, why do you use this Kelvin filter? What is the application of that filter, that Kelvin filter?
You mean why do we use common filter, not others? Or what do you mean? Why do we?
Means what we have to
Why
extract?
not Butterworth filter?
Okay.
Even notch filter.
One problem like we tried is like what happens is there's some noise from the hammer test result. Okay, we try to directly inverse this RFF, but at very low amplitude, the noise has a major effect. Well, if you inverse that, the noise is amplified. Okay, so that's the main reason, I believe. Okay, so the common filter helps us to recover the original one without minimizing. I mean, trying to minimizing the noise from this hammer test results.
So filter, you don't see any shift of peaks or something after filtering? Because the resolution is because there will be some shift, right? Some phase shift because of
yeah, phase. You mean phase shift between those two? There will be. Yeah, there will be. You're right. But the phase shift, we are mainly comparing the amplitude. We try to shift like make the experiment and they start from the. Yeah, right. Yeah.
But what do you do for runout in experimental setup? Because you will have runout.
Yeah.
live with it.
But in your FFT, your spindle frequency, I think your tooth passing frequency dominates. So
Then you are right.
Which is lucky.
No. So in my case, there have been cases where spindle frequency dominates, and
Always.
there what you would see is you would see that one of the passes gets missed. So in one half it will cut, other half it will not cut because there is more deflection.
If you see all this, we saw all this, right? That spindle frequency is dominating. And you just live with it. You can't do anything.
Yeah.
Basically, it means 80 micron. If there is not spindle frequency, will definitely dominate. Whatever you do, ideally your tool passing frequency should dominate because how much one tool is cutting, but that should be your dominant frequency. But if there is run out, what will happen is there will be a frequency, a very high peak corresponding to the
Spindle.
frequency.
Yeah.
Saw this, right?
That is not a healthy situation. So you are not cutting it right. Your machine is not.
But is it in your hand? As if you're using end mill.
So again, you forget about the spindle. It's got run out.
Yeah, this one comes from the real measurement. You see, here's the measured force. When we come back, you see, this is the first fluid, this is the second fluid. The difference between these two peaks are coming from run out. Okay? If there's no run out, they cut the same chip load. They should have the same amplitude, right?
You see your FFT in the next slide.
Yeah. You see, here's the spindle.
Okay.
This is the tooth passing. There's a spindle.
That is some.
Yeah. Okay. Okay. Now let's move to this dynamics. Okay. And because before for conventional mill we use a hammer test and use accelerometer to get this frequency response function, right? But for micromilling, we cannot do the same thing. There are two reasons. First, if we use this hammer to give a blow with a 0.5 or 0.3 millimeter diameter fluid, right? It's likely it's going to damage not the fluid, but at least the small edge at the tip, right? But the main reason is not that. It's not because of that. The main reason is even with a small hammer we have in the lab, it has a bandwidth limitation. Okay, even like with a small hammer, the bandwidth, you see, is the maximum is always below 10 kilohertz if we use -3 dB as a reference, right? With different tip, you see, with another different tip, is even the bandwidth is much smaller. Okay, so if the natural frequency of this hammer of this micromale is above that, from this small hammer we cannot capture it precisely. Okay, then we have to use other different techniques. Okay, what we did in my lab is we kind of design a customized structure. Here is a very small piezo actuator. You know how this piezo element works? Is that the piezo element, when you apply voltage, it expands. Okay, when you apply negative voltage, it kind of shrink. Okay, then when you apply this sinusoidal wave of this voltage, it kind of expands, shrink, it vibrates, right? So then we give some preload. Okay, then make this piezo fixed between this very small force sensor, which has a very high bandwidth, and the shank of this two. The cross section of this piezo element is around 3 by 3 millimeter. Okay, so it cannot attach to the tip, but at least it can be attached to the shank part. Okay, so then we apply high voltage on this piezo. Then it vibrates. It's trying to push both ends. Okay, and the small force sensor has 10 times higher stiffness than this shank here, because shank is a cantilever beam. At the tip, it's more relatively flexible compared to the force sensor.
What force sensor is this? Is it a traction force sensor or is it connected?
It's a one-direction force sensor from Kessler. Okay. Yeah. And then what happens is we put a laser vibrometer from a certain distance and measure the vibration response at the shank and the tip. Okay, so the good thing for this piezo is the piezo, it can operate at a very high frequency. For our case, we can apply up to 120 kilohertz. Okay, so then we apply sinusoidal wave of signal to this piezo from 0 with incremental frequency up to 120 kilohertz. Then at each frequency, we measure the response from laser vibrometer from the displacement of this two. Then we calibrate this frequency response function. Okay, so at the two tip. Okay, so that's how we kind of calibrate the natural frequencies, damping ratio, and stiffness for. We found out four modes. Okay.
Explain to us. You're measuring at the shank.
Mm-hmm.
You're exciting at the shank.
Yeah.
How do you get tool point at
Okay.
Because yesterday we tried. We only were interested in tool point at you excite the tool and you measure it. But here you're exciting the shank. And you're interested in tool point. Yeah. So that's how you know.
Okay, here is a kind of a micromere. So we excite at point 1. Okay, we cannot excite point 2. Okay, but we can measure here is F1. We can measure at X1 and X2, right? So we get two FRs, X1 over F1. And if we measure it, we get this cross frequency function X2, X2 over F1, right? But we know, okay, so we know there's a called reciprocity principle. Means for linear structure, X2 over F1 should be equal to X1 over F2, right? But now we are trying to see, okay, if the force happens here, okay, and the response is here. So we want to get this X2 over F2. Okay, so how do we do that? Is X2 can divide by F1 and F1 divide by F2, right? We just add this F1 here, okay? Now, how about we have this X1 over x1 again. Now x2 over f1 is what? It is frf2, right? And this is frf1.
But the cross section is not uniform, sir, at the bottom side. It doesn't match. You can.
No, so you are assuming it to be a linear.
Yeah.
Otherwise, you can't use reciprocity. So there are other ways and means to do it. There is some people use acceptance coupling, some substructure kind of a modeling.
We're going to talk about this, right?
Huh?
We're going to talk about.
I'll talk about this. I'll talk about primitive dynamics. Then I'm going
Okay, great. But basically, we use reciprocity, okay? I remember finally x2 over f2 is, if correct me if I'm wrong, is
FRF2 whole square, FRF1,
right.
FRF2 and cross whole square. FRF2 and whole square.
This square?
The cross one whole square.
Yeah, whole square.
Put
You put it in a square.
Put square here?
Yeah, square divided by direct FRF.
Okay,
And cross.
Yeah, that's it.
okay, yeah. Basically, it's coming, I remember if we follow this, it should be, this is one FRF, we know. This another FRF, we know. And this another FRF, we know, okay? Those are the obtained FRF we obtained, okay? So this gives us the results here, okay? So just some simple derivation, okay?
It's a fairly straightforward thing.
Yeah, okay,
This is the only way, I think the easier way to do it. So we talk about it.
okay, yeah, okay,
But otherwise, it's very difficult to measure these things.
okay. So that's the structural dynamics we solved. But still, the process dynamics, okay, still is a challenge. That is mentioned by Dr. Low yesterday about the process damping, okay? How do we explain process damping is now we come to this waviness, okay? Because from the chatter we know that because of vibration, the two tip generate waves on the machine surface, right? So now let's see what happens really on these waves. If we put the milling tool edge in the orthogonal point of view, we say, okay, here is the cutter edge. Okay, we first assume it's perfectly sharp in a conventional way. And it forms a chip here. Okay, if there's no waves, right, it just move straight. And if it leaves waviness here, what happens is that is a current wave, right? This is previous wave. Okay, when chatter happens, those two are not in phase. Okay, which is illustrated here. So then what happens is this edge moves to here, back to here. Okay, and my question is, first, what's this length here? Wave length here. How do we calculate this wave length? First, it's proportional cutting speed, right? Here is a cutting speed, V, times chatter frequency, chatter period, right? So which is 2 pi over omega c, correct? Okay, now we have a round edge instead. And if I draw the same thing here, and this again, this is the previous wave. So now let's think about this trajectory here. Here is a contact point, okay? Then this two, first it moves in this direction, and at the same time it has waves, okay? General wave has vibration. So here is okay, but what happens? The two is cutting to here. If I draw the two edge at this location, it becomes, you see, it's the same contact. So what happens? it's not only remove the chip formation, remove the chip here, but there's a huge contact between the two flank face and this machined surface. Okay? The flank face and this bottom edge here is trying to suppress the machined surface from the waves. Okay? As I just explained from previously, when there's a material deformation, there's a stress. Okay? There's stress and strain. Where the stress and strain, it converts into heat called energy dissipation. Okay? From the dynamics point of view, why it's become like? From the dynamics point of view, energy dissipation is modeled by damping. Okay? So basically damping means energy dissipation. That's why the indentation from the two edge to the surface, okay, this is called, we call a certain different type of damping. Okay? And now it's not coming from material of the two. It's not coming from the joint structure. It's not coming from the tooth structure. It's not coming from the shin tooth structure. It's coming from this process. Okay? That's what we call it process damping. Okay? That's a concept. And how do we calibrate the process damping force? And there are different models, but the one commonly accepted model is that its process damping force, okay, is always related to the slope of this wave. Okay? So if the slope is higher, it becomes like this. Okay? The waves. Now there is larger indentation area, higher damping force. Okay? Lower means lower damping force, which means the damping force, if I just use FD, it's proportional. We just use a C. It's proportional to the slope of this. So how do we calibrate the slope? Slope is basically the displacement y over x, right? That's how do we define slope. But since we don't know the v and x, the slope is here, and why don't we just put a y dot or x dot? It should be still the same if you take the derivative. Now, what's the y dot? Y dot is the vertical velocity in phi direction of the workpiece, okay? And what's x dot here? Anyone can tell me? Cutting speed, right? X dot is a cutting speed, right? So now, process damping force is proportional to vertical velocity and is inversely proportional to the cutting speed. Okay? So cutting speed is what? Spinel speed times the diameter of the milling tool, right? So now the diameter is fixed. That's why for lower spinel speed means lower cutting speed, which means higher process damping. That's why from the yesterday's one chatter stability, at a lower spinel speed, because the higher damping force, the stability goes to higher because we have more damping coming out from process. Okay? But the problem is there's a coefficient C, which depends on what? Depends on material property, right? Because if the two edge pressed on the harder material, there's a higher stress. It means higher process damping force. We need to calibrate C. Okay? So that part, people have done that before, and even several colleagues of mine, they do that. What they do is they press the two edge onto the workpiece slowly, okay, trying to calibrate, which I think is okay, but still it's a quasi-static way. But again, this happens at a very high speed, okay? There's very difficult to calibrate. That's why I try to run a few simulations, but not cutting, but just press in a very high speed, okay, and measure the force, and measure the force and the displacement, okay, then trying to calibrate C from the FE simulation side, okay. So that's some details about that, but here's the general idea.
Just one point. This mechanism is not unique to only micros. It
Yeah.
also happens at micros. So we did not discuss this yesterday because non-linearity is left for today.
Yeah, because for conventional machine, if the tool got blunt, right, if it has a very shallow flank angle, what happens is for very low speed, if the speed goes down, what happens to the wave? if the speed goes down, this wave is shrinked. It becomes more compact, right? For lower speed, this becomes like this, right? Now, that's much easier to have this contact on the flat face. That's why for lower speed, it has higher damping, okay? Means larger critical depth of cut for chatter point of view.
And there's a lesson in this for our cutting tool makers also. Lesser clearance angle might be better for stability.
Yeah.
Because when you have contact and then let it wear out.
The thing is that if you have 30 degrees flank out, it makes the tool-tip chip, right? So chip. But anyway, there's a balance always. Yeah. Okay, now here becomes our final topic, okay? So if you have structural dynamics and mechanics, our final purpose is trying to calibrate this chatter problem, okay? Again, this, I think now everyone is familiar. So basically, here's the milling and leave the way surface finish, and we just, based on the original equation, we add this process damping force, okay? That's the only difference. And again, this is just the explanation, like from micro machining point of view, like all the cutting force are related to based on the calibrated cutting force coefficient, which I used based on the previous two models, based on the plasticity and FE model. Like this one, I based on the slip line field model. And process damping is from the simple FE simulation, the contact to get this C value here. And also in the process, we already know the velocity. We know the vibration velocity of this two, right? So here one stable and one unstable condition. So now here is the chatter stability block diagram, right? So since we consider the damping, we add one more feedback loop, okay? And this, because it's damping, right? So it's proportional to here the displacement. It's proportional to the velocity. And here output the displacement. That's why we add, it's in the Laplace domain. S means what? A derivative, right? We first take one derivative of the displacement, which make it a velocity. Then times those coefficients and back to another feedback. So this is a process damping force plus this original force here. Now it comes to the overall force, which excites the structural dynamics, okay? Then what happens is, due to this feedback loop, it generates further headache for us to predicting the chatter stability lobe. Why? For original case, if we don't have, for the conventional machining case, if we don't have this loop, we don't have this part inside the square bracket, right? It's just I minus K A, this delay part, A times phi, okay? In zero order approximation, A is a constant because we take the average, right? So now, based on this loop, we have a new part. And this new part is also depends on the velocity, cutting velocity. Cutting velocity depends on the spin speed. We don't know yet, right? Because we are trying to get the spin speed with respect to the axial depth of cut. So how did I do is, I first assume there's no damping. I get this conventional stability lobe, okay, for different case, for original case. Then, based on each spin speed, I assign a velocity, right? So then, goes to back and try to solve this again, and get, because if you know VC, it's just the constant, okay? Then, based on that, I'm trying to update the axial depth of cut, okay? Then do a certain iteration, finally give us a real critical stability lobe here. Okay, but again, for our case, for the specific case we did before is, this is a predicted stability lobe. You can see it slightly goes up because of the process. Otherwise, it will keep constant, right, at the bottom. And we also run in a very high speed range, like from 40 to 60 kilo RPM, okay? And here we use a microphone and acoustic emission sensor to detect the vibration signal. Here you can see under.
What is the bandwidth acoustic emission you use?
This one is customized. It covers from very low, because normally the acoustic is covered very high, but not low. Yeah. Around maybe in the 1 megahertz. But this one, we ask them to customize. It can go below, I think, several kilohertz. It's also okay.
Ours is more than 100 kilohertz.
Yeah,
So what
yeah.
are we getting?
Normally, that is the case. Yeah.
We
Yeah.
make a chatter above 100 hertz, yeah? 100 kilohertz.
Okay. So basically, here we can differentiate even with like the higher spin speed, and higher depth cut. Okay, all the frequency components are in the tooth passing frequency or the two holder. But with this lower depth cut, which is normally almost like not half, but much less than the stable condition, and we have very high peak, which coming from the chatter frequency component. Okay, and here are some pictures. This is coming from the point B, and right hand side coming from point A. Okay, but point A, we take a optical microscope to see there's a lot of bursts generated because of the vibration. Okay, so those black ones, if you see, it's like very rough from the surface point of view, and also there's some marks left on the side. Okay. But anyway, I think that's the everything. So the summary is basically we're trying to determine the mechanics of the microcutting with edge radius, and based on that, predicting the cutting force, and involves identification of the two-tip dynamics. So based on that, we predict the chatter stability lobe, considering the process damping effect. Okay, so that's it. Any questions? I think we're right on time.